So molecules with a dipole moment, or dipole arrows, don't cancel out. In other words, we call these polar molecules. If the arrows do cancel each other out, we call them nonpolar molecules. So again, we realize we're falling in the range here of polar covalent. Remember, that was the difference of electronegativity. Anything greater than 0.0, so you have a 0.1 less than 2.0. In that range, between 0.1 and 2.0, any difference in electronegativity, we saw there is some movement, so we draw polar arrows, and the arrow always goes towards the element with a higher electronegativity. Remember that? So now we're going to, as we walk through this and determine if a molecule is polar or not, and this loves to show up all through the test. So again, this kind of ties it all together, being able to look at, again, bond angle, the type, first comes down to, though, being able to draw a Lewis structure. So step 1, draw a Lewis structure. Step 2, determine the shape of the molecule, and then to determine the shape of the molecule, then we'll go after polarity. We'll have to use our electronegativities here, and I give that chart to you. Remember, you don't have to memorize that. Then you're going to draw polar arrows. The arrow always goes towards the element with the higher electronegativity. After you do that, you then ask yourself the simple simple question, do the arrows cancel each other out? For example, first one example is carbon dioxide. You remember carbon dioxide, we saw in this example, carbons are central, we have 2 oxygens on the outside, ends up forming double bonds. If you remember that, remember we saw that, again, oxygen prefers 2 bonds and 2 lone pairs, so this is the most stable point. This, I have an A and I have 2 X's, so in this situation, again, if I saw this here, I would say, okay, here's my A, and here are my X's. Now, there's no lone pairs around the central atom, so it's just plain AX2. And remember, AX2, so you type up here, you put AX2. With the AX2, then we remember the shape, again, for the AX2 was a linear, and also you remember the shape, then the bond angle between my X's, this was actually 180 here between the two. So, so you must understand all this stuff. Now we haven't even gotten to the point where we're determining if the molecule is polar or not. So first of all, then we have to determine what's the difference in electronegativity between the carbon and the oxygen. I have 2 carbon-oxygen bonds, so I can form the difference between one of them, and I can use it on the other side as well. So I look at my electronegativity chart, and I provide these for you, so again, there's no memorizing going on here. You look at oxygen, oxygen is 3.5, carbon weighs in at 2.5, their difference is 1.0, so therefore their difference is greater than 0.1 to less than 2.0, therefore we say, oh, it is polar, it is a polar bond. Therefore we draw the arrow pointing towards the element with a higher electronegativity, which is oxygen in this example, and so we draw the arrow going that way and draw the arrow going that way. Do the arrows cancel each other out? Yes, they do. It's a tug-of-war match, it's a stalemate, therefore there's no movement of the flag in the middle. There's no dipole moment, and therefore the molecule is nonpolar. There's no dipole moment. Dipole moment meaning there becomes someone's gaining and someone's losing. There's no moment of that occurring here, so it's nonpolar molecule. And the arrow length, as we draw, you'll see another example, represents relative the relative quantity or the difference in electronegativity. So the difference in electronegativity is very, very slight. I'll draw a smaller arrow, and you'll see like some examples coming up here. So in the next one we have with water. Water is H2O. We look at this one, you say, oh yeah, oxygen, it's an AX2. Oh, it's linear. And you say, oh no, it's not, because oxygen has 2 lone pairs around the central atom sphere. Those lone pairs form the X's, push the hydrogens away from each other, cause them to be bent. Remember that? Bent. Bent is I have an AX2E2 in this situation, and the shape ends up being the bent ends up being bent, and the bond angle on this one was 104.5. Okay, so good job. So again, you need to know all this stuff. Make sure you understand it. So in this one, I say, okay, I have an AX2 and I have E2. Now I have oxygen. Now I'm determining if my bond is polar or not. So I have an oxygen and hydrogen, and so I look up their electronegativities. And I'll do it for 1, because I'm going to apply it to the other. Oxygen weighs in at 3.5, hydrogen weighs in at 2.1. Their difference in electronegativity is 1.4. It's greater than 0.1, less than 2.0. Therefore, again, it's a polar molecule. Therefore, I draw polar arrows. Now, I'm going to draw the arrows going towards the oxygen. So if you go into this situation, realize that the arrows do not cancel each other out. It's like two rivers joining and forming into one river. The overall movement is up above. So what happens up here, above my oxygen, I may become partially negative, and below my down by my hydrogens will become partially positive. And this is very, very important you understand this. So what we'll do here, we'll draw out this situation. It's very, very important you understand this. Up here I'm becoming partially negative, and down here I become my partially positive. And so this is, I have a dipole moment. I have a moment where there are charges. Someone's gaining, someone's losing. Therefore, I would classify this molecule as a polar molecule. Water is a polar molecule. And that makes sense because we realize, oh yeah, water is a universal solvent. And so it can dissolve salt. So it must, like, has ions, has positive and negatives. Therefore, we see that these partial charges of water allow it to be that universal solvent. And again, give the positive and negative, partial positive and negative charges. However, it's still a covalent compound. Next one we have is boron trichloride. Remember, borons in group 13 only wants have 3 valence electrons, only wants 3 bonds. So if you say, oh, I'm missing a bond, you have Lewis structures here, you're wrong, because one of the single bonds does not become a double bond. Boron only wants 3 valence only has 3 valence electrons, only wants 3 bonds. This one we look at and say, oh, I have an AX3, therefore it is a trigonal planar, therefore the bond angle is 120. So in this situation, again, we have a boron and a chlorine. I have 3 of them. So I'll just calculate one boron, chlorine, I can apply it to the rest of them. So the difference here, I look it up on my chart, their difference is 1.0, therefore greater than 0.1, less than 2.0, therefore there's polar molecules. So I draw my polar arrows in here. Now you have to understand this is a perfect triangle, so you can't necessarily see it with the arrows perfectly there, but the fact is, being a triangle, all of the chlorines are equally pulling away from the boron, therefore the arrows cancel each other out, and the molecule is nonpolar. Now, that's the key thing. If on all ideal geometries, as long as your x's are the same, it will always be nonpolar. All ideal geometries, as long as the x's are the same, it will always be nonpolar. Key thing. And also understand that once you have that valence, once you have a lone pair somewhere, commonly, if it's not, will become actually a polar molecule. And the next one we have down here is carbon. We have 2 hydrogens and 2 fluorines. So I actually have an AX4. But remember, I told you, as long as your X's are all the same, they're not the same in this situation. We have 2 bonds we're going to take a look at. We're going to take a look at, this again, trigonal tetrahedron, a 109.5. But we're going to look here, we're going to see that, well, I have a fluorine and a chlorine. The difference there is 1.5. Therefore, it is very, very polar. My hydrogen and my carbon, though, it's not much of a difference. It's actually 0.4. So I'm going to draw a smaller arrow here. But we also see that, again, my arrows are going to be moving towards my carbon. So in this situation, as my arrows move towards my carbon, my movement's going towards my carbon, but then I realize it continues to move that direction. It doesn't stop, it continues to move because now the fluorines pull out. So my overall movement is in that direction. So what's happening now is on that side of my molecule, I'm becoming partially, again, I'll draw this out here, I become my partially negative here, and I become partially positive here. I have a dipole moment, therefore I have a polar molecule. Make sure you're able to do this. Again, as you see from this, all starts out being the draw the Lewis structures. A couple more examples here. We have xenon, and 2 fluorines. But again, we have here an AX2E3. Remember I told you any additional lone pairs or extra electrons, always put them around their central atom. And I told you before that we can have noble gases, as they get larger, can form bonds. And they come in contact with something with very high electronegativity, like our fluorine. And so our fluorine causes it to forms a bond there, but now we have an AX We have an AX2E3, AX2E3, and this is one of the shapes I told you to memorize. We see now the lone pairs actually form, stay on the same plane and form a trigonal planar between the lone pairs, but it forces one fluorine to go straight up, one fluorine to go straight down. So the bond angle between my X's, ends up being linear, ends up being a 180 degree. So in this situation, the fluorine's pulling up, one fluorine's pulling down. They actually a tug-of-war match. Again, there's no movement of the flag. Therefore, this molecule there is no dipole moment. Therefore, it is a nonpolar molecule. Next, we'll look at is NH3. Now, NH3, remember again, you see, oh, that's an AX3. Well, no, remember, nitrogen has 15, has 5 valence electrons, has 3 bonds with the hydrogen, but it has that lonesome lone pair out there. So you must remember that lone pair. And that lone pair actually forces everything down to form a trigonal pyramid. In this situation, a trigonal pyramid. So here's my triangle, but no longer is a trigonal planar because that lone pair is pushing down to a trigonal pyramid. Now, in this situation, we have a valence. We have in the Vespel theory, because we have our valence electrons, our lone pairs appear in the central atom. Therefore, it's thrown out of the ideal geometry. Therefore, the arrows will not cancel each other out. We have a difference between the electronegativity of hydrogen and nitrogen. It moves towards nitrogen, they continue movement straight up. So in this situation, again, what we're going to find down here is that the bond down here is where we're going to be partially positive, and at the top up here, above the nitrogen, is where we're going to be partially negative. I have 2 poles. I have a dipole moment. Therefore, this molecule is a polar molecule. So I have a dipole moment. Therefore, the molecule is a polar molecule.